We have looked at how to compute the derivatives of inverse functions if we know how to find the derivative of a function. Now we also know how to find the derivative of its inverse function. And we have found already the derivatives of log x, which is the inverse of the exponential function, and sine inverse x, which is the inverse of the sine function. I had asked you to find the derivative of cos inverse x, and this differentiation that you do for this is very similar to what you do for sine inverse x, which you already seen. So the answer here, I'll just give you the answer, and you can ask me if you did not get this answer or you got a different answer, then we can look at it. But I think everyone has already got the same answer. The derivative of cos inverse x is minus 1 upon square root of 1 minus x square. The procedure is the same as before. You take y is equal to cos inverse x, so x is equal to cos y, and then differentiate that, take the reciprocal and substitute for x. That is, you would have got minus 1 by sine x, sine y as the reciprocal of the derivative. So sine y is square root of 1 minus cos square y, and cos y is x. So this will be the final answer. Okay. Then similarly, you can find the derivative of tan inverse x. Then let's see. Of course, cot inverse of x, which will be similar to this. And secant inverse of x. And cosecant inverse. Okay. So these are all inverse trigonometric functions, all the basic inverse trigonometric functions, and we'll find all their derivatives. So let's start with tan inverse x. So we write y equals tan inverse x, which means x is equal to tan y, and therefore dx by dy is equal to derivative of tan y with respect to y. We know the derivative of tan is secant square, so this will be secant square of y. Now remember, the final answer has to be in terms of x, because we are differentiating tan inverse x, and y is the label that we have given it. The final answer should not have y in it, and if possible, it should be written in the simplest form possible. As in, you could of course write secant square of tan inverse x, because y is tan inverse x. That's correct, but it's not the simplest form possible, because you are actually applying a trigonometric function to the result of an inverse trigonometric function. So the final thing should be actually an algebraic function. Okay, so let's see if that is possible. So if you can remember the identities, we used this identity, sine square x plus cos square x equal to 1, in order to find the derivatives of sine inverse x and cos inverse x, because in the final step you will get, if you're differentiating, for example, cos inverse x, as I said just now, you will get minus 1 by sine y. And so we use the fact that sine y can be written as square root of 1 minus cos square y. Okay, so this is just any variable, it does not x in particular, so any theta. Okay, so here we'll take minus 1 by sine y, so that is in the position of sine theta, so that will be equal to 1 minus cos square theta under root. So that's how we get this. Similarly here we need to express this secant square in terms of tan. So how do you get secant in terms of tan? If you remember the identity, 1 plus tan square theta equal to secant square theta. Okay, you can remember that. If you don't remember it, you just need to remember this, and you can get that one from this. So how do you get the other identities from this? Yeah, secant square x is 1 plus tan square x. How do you get that identity from this if you don't remember it separately? How do you get it from this? You remember this, and then we want tan, right? So here you have sine and cos. What is the relation between tan theta and sine theta and cos theta? Tan theta equals sine theta divided by cos theta. So here you already have sine. So divide by cos square theta. So sine square theta, if you throw out divide by cos square theta like this, then this becomes tan square theta. This is 1. Okay, cos square theta by cos square theta. And over here you have 1 divided by cos square theta, which is secant square theta. So from this you can write secant square y as 1 plus tan square y. But what is tan y? Tan y is x, because y is tan inverse x. So this is 1 plus x square. Okay, so that dy by dx is equal to the reciprocal of dx by dy. That is our property that we are using here everywhere, which is 1 by 1 plus x square. Therefore, the derivative of tan inverse x is 1 upon 1 plus x square. Okay. Now this one you should do in a similar way as homework. I'll write the answer now, but please do try it later as a further practice for the same kind of derivation. So here you will get minus of 1 by 1 plus x square. Okay, you can see the similarity. For sine inverse x, the derivative was 1 upon square root of 1 minus x square, and for cos inverse x you have minus 1 upon square root of 1 minus x square. And similarly, remember derivative of sine x is minus cos x, and sine x derivative is cos x, and cos x derivative is minus sine x. Similarly, tan x derivative is secant square x, and cot x derivative is minus cosecant square x. So the same kind of relation holds here. Tan inverse x derivative is this, cot inverse x derivative is minus of that. Minus is the same thing. So you would expect similar results here also. But you have to first find derivative of secant inverse x. So again we take y equal to secant inverse x, so that x is equal to secant y, and therefore dx upon dy. And what is derivative of secant theta? Secant theta tan theta. So here you get secant y tan y. Okay, now we need to write this in terms of x. So this secant y is just x itself, so no problem with that one. You don't have to do any additional conversion. Secant x is exactly tan x. I'm sorry, secant y is exactly x. But now you have tan y remaining. So what to do with this tan y? We have already this identity. Tan square theta plus 1 is secant square theta. So what is secant square theta? It is, so how do you get, I'm sorry, we need to get tan theta in terms of secant, because here you have tan, right? We want it in terms of secant. So here tan square theta is equal to what? Secant square theta minus 1. Correct? And therefore tan theta is square root of secant square theta minus 1. So this is square root of secant square, in this case secant square y minus 1. But secant y is x. So this is x times square root of x square minus 1. So this implies dx upon dy is reciprocal of this. So that. So this would be 1 upon x times root of x square minus 1. I hope this is also clear. And so you can now guess cosecant inverse x has the derivative minus of 1 upon x times root x square minus 1. So again, you have to prove this, okay, verify it by differentiating in the same way. We are guessing for now, but you have to verify it. So these three are homework: tan inverse x, cot inverse x, cosecant inverse x, and yeah, okay, those two you can do as homework. We already done cos inverse x. So I hope these are clear. These are all the derivatives that you find by using the inverse function differentiation method. So now you can find more derivatives involving these functions also. So for example, and using the previous properties that we looked at. So for example, what would be the derivative of tan inverse e power x? Okay, so we'll write these exercises and maybe do them later. Then derivative of 1 by sine inverse x. So again, remember this notation. You have to be careful with the notation. Normally we write a inverse to mean 1 by a, but for in this case we are writing the inverse of the function and not the reciprocal. So 1 by sine inverse x is not equal to sine x, obviously, otherwise this would be, we don't need any different method for this. We would be just finding derivatives of reciprocals. That's not the case. So this is 1 upon sine inverse x, not, which is not equal to sine x. Okay, so this is reciprocal of the inverse sine function, so sine inverse of x, and you will have to use quotient rule or chain rule for this. Yeah, so this one's derivative of cotton was of 1 by x, and we know how to differentiate log as well. So let's try that. Derivative of x times log x. Okay, so we'll try these problems later. You can try them as exercise, and maybe in the next hour we'll solve one or two of these. Now we can differentiate all kinds of functions now, using all the properties that we have looked at so far. So that is chain rule, product rule, quotient rule, then differentiation of inverse functions. So using all of these, combining all of these, you can differentiate any kind of function. So let us look at an example. How would we differentiate, say, 3 to the power of x? This is not a polynomial. So if it was a polynomial, you would have terms of the form x to the power n, and their differentiation, as you know, is n x to the n minus 1. So any term of this kind can be differentiated easily. This is one of the first derivatives that we obtained. So this is not difficult, but this is not a polynomial. Here you have 3 to the power of x. So what kind of function is this? Is actually an exponential function, not the exponential function e power x, but this is also exponential because it is something raised to the power of x. So the variable of differentiation is x, and that x appears in the exponent here, right? Not in the base. Here it is appearing in the base. So these may look similar. So if I write x cube instead of 3 power x, in some way they are similar, something raised to the power of something. But what matters is whether the variable of differentiation is in the base or the exponent. Okay, so you wait, what are you asking? 3 to the 3x to the x minus 1. No, it's not. That's the thing. It is not, the answer is not. So if it was in this way, then you might guess it is x times 3 to the x minus 1, or you have guessed 3x times x to the x minus 1, maybe because of chain rule. But that's not it, because it is not x to the n, it is 3 to the x. So this is similar to, if anything, it is similar to e to the power x, right? Because there also you have x in the exponent, not in the base. Only problem is this is not e, right? This is a different constant. So we know that derivative of e power x is e power x itself. Okay, but what if you had e to the power of ax? Then this would be a e to the power of ax. So even this can be differentiated. Sorry, even this can be differentiated. Here we have 3 to the x. Is there any way in which you can write 3 in terms of e? So you can observe this. What is e to the power of log of a? Remember that exponentiation and logarithm are, that is the natural logarithm, these are inverse functions. So if you first find the log of a and then take e to the power of that result, what should you get? Yes, this answer should be A itself. So the answer to whether you can write or how do you write 3 in terms of E is this. 3 is equal to e to the power of log 3. How does that help? Now what is 3 power x? It is e to the power of log 3 to the power of x. But a to the b whole to the power c is a to the bc. So this is e to the power of log 3 times x. And now you can see that we have the same thing here with a equal to log 3. So if you differentiate this, what will you get? You're differentiating this e to the log 3 times x. So e to the ax differentiation is a e to the power ax. So here a is log 3. So you should get log 3 e to the power of ax, that is again log 3 x. Now to write this in a nicer form, already we know e to the power of log 3 times x is 3 to the power x. So the final answer is 3 to the x log 3. Okay, so that is the answer here. 3 to the x log 3. Is e to the power of log a equal to a function? No, that's not a function as such unless you consider a variable. So here we are considering a to be a constant. So e to the power of log a equal to a is just a property of log and exponential because they are inverse of each other. So we are just making an observation. You can write e to the power of log 3 equal to 3. Right? So for any a, so we are not considering this as a function of a. It's true for all a. So we are considering a as some unknown constant. Okay, because I don't want to say function because we are differentiating with this function with respect to x. So we are considering x as a variable, a as a parameter. That's only a point of view. You could call this a function if you wanted of a, which is true. Only we are not considering that. We're not interested in this as a function of a. We are interested in this property, in this relation. Okay, so we get d dx of 3 to the x is 3 to the power x log 3. Now you could have, instead of x here, you can have sine x. So I could ask what is derivative of 3 to the power of sine x. So it can be done in the same way. But there is also another way to write this. Okay, because the only thing is here, whatever you get in this form, in basically an exponential form, you will have to rewrite it as e to the power of something, right? So to make the writing easier, because here, if you have a more complicated function here, everything will be there in the exponent. And so at least it's difficult to write and to think about. So we have what is called logarithmic differentiation, which is not any anything that gives us the ability to differentiate different functions, because we already have it. We already can differentiate this kind of function using this technique. So it's just a different way of writing the same thing. It's not really a new technique like chain rule or inverse functions. Okay, this is the same thing written in a different way. So in logarithmic differentiation, what we do is make this observation. If y is equal to any function of x, then log y is log of that function, obviously. Now differentiate both sides with respect to x. So we find derivative of log y with respect to x. Okay, but what does that mean? We have to use chain rule. So ddx of log y is actually equal to ddy of log y multiplied by dy upon dx. This is simple chain rule, right? We know that y is a function of x. So ddy of log y is ddx of log y is ddy of log y times dy by dx. What is ddy of log y? It is 1 by y, and so this will be 1 by y dy by dx. What we want is dy by dx. So in this case, y would be equal to 3 power x, and we want to find dy by dx, which we now know is this. So we want to find dy by dx. So then from this we get dy by dx is equal to y times ddx of log y. Okay, this works for any function. It doesn't have to be written in this form, some constant to the power x. It can be any function. You can take log y and then differentiate and then multiply that by y itself. So this always works. So the point of using this, or when do you need to use this, or when is it preferable to use this? If indeed y is an exponential function of some sort, that is 3 power x, or some even say sine x to the power of x, even in that case, because you have a function in the base but also in the exponent. Okay, not a constant in the exponent, you have a function in the exponent. So then you would need to use it there also. We'll see examples of that. So in any such case, this is preferable rather than doing this, because writing becomes simpler. But you can also use this for other functions. So if you simply have let's say 1 divided by x times 1 plus x times 2 plus x, you can do it by using product rule and chain rule or quotient rule. But this is also a different way of doing it, which will give you the answer in a simpler way. We'll see examples of that. First, let us look at when you're almost forced to use it. That is when you have functions of this kind. So I'll repeat the same problem with this, just so you can see how it goes. So now let us try to find derivative of 3 to the x without using the answer we already got. So we write y is equal to 3 to the x. Then take log on both sides, that is natural log. So log y is equal to, now what is log of a to the b? B log a. So this will be x log 3. Basic properties of logarithms which you need to remember. Differentiating both sides. On this side, you know that log y derivative is 1 by y divided by dx. So you can just use that. Okay, use chain rule. Immediately you get 1 by y divided by dx. And on this side, log 3 is a constant. Although we are writing log, which is a function, it is applied to 3, which is a constant. So log 3 is not a function. Okay, do not write derivative of this is 1 by 3. This is a constant. So log 3 is constant. So it is ax, where a is log 3. So derivative of that is just a. So this is just log 3. Okay, right hand side becomes just log 3 when you differentiate with respect to x. And therefore we have dy by dx is y log 3. That is derivative of 3 to the power x is equal to, that is y. Now what is this? 3 to the x. Okay, so you get the same answer as before, but maybe it's slightly easier to write. Particularly in the more complicated functions, you will see that this is easier to write than writing everything in the exponent and doing the computations there. This is understood. We'll look at another example. I'll write another example here, so we can see that in parallel. So instead of 3 to the x, let's say you have 2 to the sine x. So it's not just x in the exponent, but some other function of x. So again, start by writing this as y. Y is equal to 2 to the sine x. What is the question? Derivative of log is log itself. No. Where is that? Derivative of log is 1 by x, right? Or derivative of log of something is 1 divided by that. Where do you see derivative of log equal to log? If you're talking about this, remember we are differentiating with respect to x, which is a variable, and log 3 is a constant because 3 is a constant. So this is actually derivative of ax. This is ax. So when you differentiate, you will just get a. Right? This is a. It's a constant. Are you asking about something else in this? Derivative of log here, right? That is by chain rule. We did this in general here. Derivative of log y with respect to x. So you have to apply chain rule and make it derivative of log y with respect to y multiplied by derivative of y with respect to x. So for example, suppose you had to differentiate log of say 1 plus x square. So directly you cannot do this from first principles, right? So what we do is write this as this 1 plus x square will be taken as one variable, and you differentiate with respect to that to get 1 upon 1 plus x square, right? Because derivative of log of something is the reciprocal of that. But then you need to apply chain rule, so you will be multiplying by derivative of whatever is inside the box, and that is derivative of 1 plus x square, which is 2x. Actually, we usually write it in the other order as I prefer. 1 plus x square derivative is 2x, and then derivative of log is reciprocal. Okay. Fine. So coming back to this problem, we need to find derivative of sine 2 to the sine x. So differentiate 2 power sine x. So again, take this to be y. Then apply log on both sides. So log y is equal to, careful when writing this, the sine x in the exponent comes down when you take log. So you get sine x log 2. Okay. And be careful, this is sine x here and then multiplied by log 2. The log 2 is not inside the argument of the sine function. Now in all of these problems, the left hand side is always the same. You start with log y and then you differentiate to immediately get 1 upon y dy by dx. That's never going to change, because you'll always take this to be y and then take log. So this will be y, then log y, then 1 by y dy by dx. LHS is always the same. Now on the RHS, what happens? Again, log 2 is constant. So you have sine x derivative is cos x. Okay, I'll write this here. So then dy dx is equal to y cos x log 2. But again, don't let y remain in the answer. So y is 2 power sin x, right? So 2 power sin x times cos x log 2. Okay. So I hope this method is clear. Now we can do more complicated problems on this, because here we have kept the base constant and only the exponent is a function. So you can of course take more complicated functions like inverse trigonometric functions or composite functions here. But apart from that, if you take the base also to be a function, which is very well possible, then you will get something a little more complicated. So let's look at an example of that. So suppose now that you need to find derivative of, so this is one of the basic examples, x to the power of x. What kind of function is this? You have, it's neither polynomial, it's neither x to the power of some constant, nor the usual exponential function where you have constant to the power of x, right? Here you have x, the variable, to the power of x itself. So both the base and the exponent are functions of x, namely x itself. So the same technique works here. Then you take y is equal to x to the power x and take log. So log y is equal to x log x. So this was one of the exercises, right, that I gave just now. We will be doing that now. The RHS differentiation will be the answer to that exercise. So now LHS as before is 1 upon y dy by dx. As soon as you differentiate, you get 1 upon y dy by dx. And on the RHS, what do you get? Now you need to apply UV rule, because this is a product, right? What is derivative of x log x? If it was just log x, then yes, it is 1 by x. But here you have x also. So by product rule, you should get x times derivative of log x plus derivative of x times log x, correct? X times derivative of this plus derivative of x times log x. What is derivative of log x? That is 1 by x. And what's derivative of x? That is 1. And so this is x times 1 by x, that is 1, plus here you have log x. Is this clear? Simple UV rule. On the RHS is just simple UV rule. Forget the logarithmic differentiation. Once you get this, it's just UV rule. So you have dy by dx is y times 1 plus log x. Y is x to the x. So here you have x to the x log x. So that is the answer. Okay, I'll summarize it and write. The answer that we get here I'm sorry, I forgot I don't know what I did. 1 plus log x. I missed that. Yeah, x to the x 1 plus log x. Is this clear? So it's because we have x in the base as well as the exponent. So what you should try as an exercise is x to the x to the x. Now let me tell you the convention when you write a to the b to the c. There are two possibilities for this, right? Because I have not used brackets here. There are two possibilities for what this can be. It might be a to the b whole to the power of c, or it might be a to the power of b to the power c. Are these the same? No, because exponentiation is not an associative operation. Okay, so these two are different. But which one of these is this? So just a matter of convention. What do we normally define it as? We define it to be this and not this. Why is that so? Or is that sometimes you just have to adopt one convention arbitrarily, right? But there is a slightly good reason for why this is the convention rather than this. And that is because this doesn't need to be written in this way. It can be written as a to the bc because of the law of exponents. If you ever need a to the b whole to the power of c, you can just write a to the bc. So normally you never need to write this for never need to write this. So remember, this is the parenthesization of this is like this. Here you have, even if that is not given, this is how you write the parentheses. It is x to the power of x to the power x, and not x to the power of x whole to the power of x, which would be simply x to the power x square. Okay, that can be given as a different question, although a simpler one. So I can also ask, what is x to the power of x square? Okay. So again, here also you have an exponent, so you need to understand this is x to the power of x square. Okay. You understand the need for the convention here, right? There are two different possibilities, and this is it. This is the representation. All this is the representation of this, not this. So the need for the convention rises from exponentiation not being associative, and we favor this as the convention, or this has been adopted as a standard convention because this one. You never need to write this. You could always write a to the bc instead. So this is better. Okay. Similarly, you know that if you write a minus b minus c without brackets, is this equal to a minus of b minus c? No. Again, because a minus of b minus c is just a minus b plus c, right? So what this means is a minus b minus c. So this is also a convention. You can see that it's opposite of this convention. Here you put the brackets first, here you put the brackets here. So you say that this notation is right associative and this notation is left associative. You start putting brackets from the left. Okay. So here you take y equals x to the x, and so that log y equals x to the x log x. Now, if we had not done the previous problem, this one, we would have to take log again because there is still an x to the x here, right? So in this one, we don't actually need to do that because we can use this result. We already know the derivative of x to the x is x to the x times 1 plus log x. So using that, what I'll do is differentiate immediately. So 1 upon y dy dx equals, so let me write it first, x to the x ddx of log x plus log x ddx of x to the x. Now here you have derivative of log x is 1 by x. So x to the x times 1 by x plus what is this? Derivative of x to the x. That's what we have here. So that will be x to the x 1 plus log x. Okay, note that this is equal to this. Okay, this differentiation is just this, so simple enough. This differentiation, the second one, is equal to this from the previous result. If that was not there, you would have to do this separately, right? I don't really recommend taking log again here, even if you don't remember this, or if you're not expected to know this actually. So don't take log here again. Instead, do it this way, right? Till here, and then for this you do it separately. Take some, let's say z is equal to x to the x, log z is equal to x log x, then similarly find the derivative and then substitute here. So if you've done that, this is what you will get. So let me just finish it here. So this is the answer. You can just simplify it a little bit if you want. Here you have x to the something divided by x. So that's x to the x minus 1, right? X to the x and divided by x to the 1. So that's x to the x minus 1. Here you have, plus x to the x, then log x, and then 1 plus log x. Okay. This is not the final answer. This is 1 by y dy by dx. And so dy by dx is equal to y times of this. But what is y? So I'll not write an addition step because of lack of space. Y is again the original function, this one. So I substitute that here and then multiplied by this. So x to the x minus 1 plus x to the x log x 1 plus log x. Okay. So if you want, you can further multiply this inside and get x to the x plus x minus 1 plus x to the x plus x to the x, because all these will get combined, and then these. We have so far been looking at functions that can be written as y equals f of x. We know that sometimes we write functions in a different way. So when you do coordinate geometry, you will write the circle equation as, so a simple case, the circle centered at the origin, you write it as x square plus y square equal to radius square. So let me take radius to be 1 here. You write this, right? Now this allows us to write or compute the value of y given a value of x. So if I give x equal to 1, then you get 1 plus y square equal to 1. So y square equal to 0. So y equal to 0. If I take another value of x, say x equal to 0, then you get 0 plus y square equal to 1. Y equal to plus or minus 1. So given any value of x, you get one value or one or more values of y. If you always take one value of y from that, what you have is a function. So the problem is this is actually multi-valued. So strictly speaking, y is not just a function of x, because as you can see, if I put x equal to 0, you get y equal to plus or minus 1. So if it's multi-valued, it's not really a function, but we can always restrict to, say, taking only the positive square root. So I can take y is equal to actually what? Plus or minus square root of 1 minus x square. Now if I say cancel one of these, so if I take, it's not really an implication then, if I take y equal to plus square root 1 minus x square, that gives me a function of y, well, function of x as y, right? So in fact, this would be just the upper semicircle. If you plot it, you will only get the upper semicircle here. Okay, so this would be this function. And if you take negative square root, you will get the lower semicircle. So this is a valid function of x now. So you can find its derivative. So of course, if you differentiate y straight away, you get, if you apply chain rule, you are going to get minus x by square root of 1 minus x square. Okay, you can try that. You get minus x by square root of 1 minus x square if you differentiate this. But the question is there any way of finding that derivative without solving for y first? So in particular, suppose the function was very similar, say x cube plus y cube equal to y. Okay, so I've changed these to cube and I've changed this to y instead of a constant. So now you can't actually solve for y because it's a cubic equation, right? There are methods of solution of cubic equations. Still, it's difficult. And again, I can write maybe x power 5 and y power 5 here and some y square here. Then you get a fifth degree equation, which you cannot solve. Okay, so in that case, is there a method for finding the derivative of y with respect to x without solving for it? So that is the problem of implicit differentiation. Okay, so yes, you can do it. You will get the answer, the derivative also in terms of x and y both instead of just x, but that's possible. So that we'll look at next. So an implicit function of x and y, or x in terms of y and y in terms of x, that is a function of this form. You have f of xy equal to, I'll write equal to 0. Okay, there's no, you can write equal to constant, but equal to 0 is also fine. There's no loss of generality in writing that, because if you have a constant on the RHS, you can always bring that over to the LHS as subtraction and then call the resulting LHS f of xy. So for example, if you had x square plus y square equal to 1, you can write that as x square plus y square minus 1 equal to 0. So this f of xy would be that entire thing, x square plus y square minus 1. Okay, so implicit, this is implicit function. So our function here is not f. F is a function of two variables, x and y, but that is not the one we are calling the implicit function. This the equating the function xy, function f of xy to 0 gives a relation between x and y. So again, as an example, let me remind you the circle equation, which I'll rewrite in this form. Okay, this gives an implicit function of y in terms of x or x in terms of y, whichever you prefer. As in, if you substitute for one variable, you get values of the other variable. So implicitly, y is defined as a function of x. At the same time, x is defined as a function of y, depending on which you take. Okay, which you take as a dependent variable and independent variable. So in differentiation, we often talk about dependent and independent variables. So dependent variable means a variable that whose value depends on one or more other variables, that is dependent. An independent variable is one which takes values independent of any other variable values. So again, usually it's a matter of perspective or point of view, which you call dependent and independent. So if you want to treat x as a dependent variable, the idea is you give values to x independently, like all possible values. So in this case, you can give any value for x between -1 and 1. If you give any value larger than 1 or smaller than -1, y will not be defined as a real number. Why? You will get complex roots for this quadratic equation. So we want real numbers. So you can give any value for x between -1 and 1, and then get values for y in terms of that. So you will call x a dependent, x an independent variable and y a dependent variable. Okay. And vice versa, you could choose y as the independent variable and x is the dependent variable also. So you will fix one of those as dependent and the other as the independent. Then you can ask for derivative of the dependent variable with respect to the independent one. So suppose you want to find dy by dx. So we are treating y as the dependent variable and x as the independent variable. Question is how to find the derivative if an implicit function is given. As I said, in this simple example, you could solve for y in terms of x. You can write y is equal to square root of 1 minus x square, or else minus square root of 1 minus x square, and then differentiate it as you should. But what if you have a function where you cannot do that? Okay. So for example, sine of x plus y plus sine of x minus y equals 1. So you definitely cannot solve for y in terms of x or x in terms of y there. So how to differentiate in that case? So what we do is, if we have fixed x as independent, we just differentiate the LHS and RHS. RHS is 0, so it remains 0. LHS, when you differentiate, how do you differentiate? You have some expression in terms of x and y, like this. Now, if it is just in terms of x, you're differentiating with respect to x. So if you if the term is just in terms of x, you can differentiate it normally. If it is in terms of y, then you can still differentiate it by using chain rule. And we have already done this. If you have log y is equal to something, what is its derivative with respect to x? 1 by y dy dx. So the same way, here you can do implicit differentiation. That is, for example, if you have x square plus y square minus 1 equal to 0, just differentiate. So differentiating with respect to x, okay, you don't have to write this. You get 2x. Derivative of x square with respect to x is 2. Okay, maybe I'll write the step first. Just for the first problem. Remember, all the terms are being differentiated with respect to x. Do not write d dy here, because you're differentiating throughout with respect to one variable. That one variable being x here. Okay, right hand side is clearly d dx of 0 is 0. So I'm not writing that. Here also this is 0. Okay, fine. Now, derivative of x square with respect to x is 2x. What is derivative of y square with respect to x? We'll have to use chain rule for that. So this is actually d dy of y square times dy by dx. Okay, chain rule, right? So d dy of y square is 2y, and what is dy by dx? We don't know. The point of the implicit differentiation is to find that. Yeah, so you get 2y dy dx. This of course 0, the next term, and the right hand side is 0. And so now you get dy upon dx is equal to, taking 2x to the other side, you get minus 2x, and then dividing by 2y. So this is minus of x by y. And so the answer here is in terms of both x and y, and now it's not wrong because you're not given y as a function of x explicitly, you're given an implicit function. So it's fine to write minus x by y. Okay. Of course, again, in this particularly simple example, you could write minus x by square root of 1 minus x square. But that's actually more wrong than right, because y could also be minus square root of 1 minus x square. So it depends on the value. But y has two possible values for x. So when you do this, this works for all possible values of y in terms of x. So this is a better answer in the case of implicit differentiation. Now let's look at this. So remember that derivative, if you evaluate the derivative at a point, what you get is the slope of the curve. So let's see if we get that. So this actually, this equation represents a unit circle centered at the origin. Unit circle meaning circle of radius 1, right? So using this, you should be able to find the slope of the tangent to this circle at any point xy. So first, let's take this point. So what is this point? 0, 1. So at this point, dy by dx equal to minus x upon y, that is minus 0 upon 1, right? So I'm actually finding this at the given point, not at a general point. So it is minus x upon y, which in this case is minus 0 upon 1, so that's just 0. So this says that the slope of the tangent at this point is 0, which is of course obvious if you know the basic properties of circles, because this is the radius, tangent will be perpendicular to that. So the tangent is parallel to the x-axis, which means of course that its slope is 0. But for the same x, you have another possible value of y, which is here 0, minus 1, right? So at this point also, the slope will be minus of 0 upon y is now minus 1. That's still 0. Okay. So you can find the slope at any point on the circle. Okay. Now let's try this point. Here it is. The coordinates are 1, 0. And so the slope will be minus 1 upon 0, that is minus infinity. Okay. Now, as far as it's a slope of a straight line, doesn't matter whether it's plus infinity or minus infinity, because the straight line will look the same no matter what. Okay. So you can also say it is infinity. So that's clear because this tangent is parallel to the y-axis, right? This is parallel to y-axis, perpendicular to x-axis. So indeed the slope is infinity or minus infinity. Now, if you ask why we are getting a negative sign, that's if you imagine that you are going in the increasing direction of x. So starting from 0, if you go in the increasing direction of x, you will start at this point and you're moving downwards, right? So when you're going forward, here the slope is negative everywhere. Here it is perfectly 0, and then it's starting to slope downwards, right? Again, as in the usual case, imagine that you're walking down this circle. Okay, so as you go in the increasing direction of x, the slope becomes steeper and steeper downwards, not upwards. So technically, this is a limiting case where you reach this point. This is perfectly vertical. But since you have been going on a negative slope all this time, you can say that it makes sense to say the slope is minus infinity rather than infinity. Or in other words, if you try to stand here, you would just fall down, right? Because there's nothing supporting, there's nothing giving normal force upwards. It's perfectly flat at this point, exactly, right? Not anytime before or after. At this point, exactly, it is negative. I mean, it is zero. The normal force is zero, right? Upwards force is zero. It's perfectly vertical, right? So you can say it as minus infinity because you're moving in this direction. Whereas if you find it here, you will get positive infinity. But of course, it's the same line, basically, it's the same line at different points. But again, the slope is positive infinity because here you have to climb directly upwards to get started on this, right? When you're moving from left to right. But you can see that it's easy to find the slope using this, using implicit differentiation in case of a curve given implicitly. Even if you don't understand the geometry too much, it's okay. Just learn this procedure for now. We'll look at applications later if there is time. Okay, so to take another example, let's take simple one, e to the xy equals 3. So again, this is one where you can solve. If you take log on both sides, you will get y in terms of x. But if you're asked to differentiate it implicitly, if you're given it in this form and asked to find dy by dx, it's understood that it's implicit differentiation. So you don't need to solve for y first. Just differentiate. So differentiating on both sides, you have to use chain rule. So you get e to the xy times derivative of xy. What is derivative of xy? Product rule. It is uv rule where u is x and v is y, say. So x times derivative of y, that is only dy by dx because that's unknown, plus y times derivative of x, that is 1. And on the right side, what you have, right hand side, what you have, differentiation of this is 0. Remember, it's differentiation. It does not remain 3, but differentiating it, so you get 0. And okay, now this is a product equated to 0. So you have two possibilities, either e to the xy is 0 or this is 0. And your aim is to find dy by dx. So you should take this is equal to 0. Okay. So you get x dy by dx plus y equal to 0. So that dy by dx is equal to minus y upon x. Now, as I said, you could write xy is equal to log 3 to the base e, and then you will get y is equal to log 3 upon x. And so if you differentiate that, you get minus log 3 by x square, which is exactly what this is. Okay. So again, this is just a simple example. Now, suppose you have a function where you cannot solve for x or y. So then your only option is implicit differentiation. The other option is not there. So you have, let's say, sine of x plus y plus cos of x plus y. I think earlier I said sine of x minus y. There actually you can use some trigonometric identities to simplify it. So I won't take that one. Let's take this. Sin x plus y plus cos of x plus y equal to 1. Now, really, you cannot solve for y because you have sine and cos. Even if you take sine inverse, for example, here you get x plus y and you get sine inverse of cos of x plus y. And you cannot do anything further with that. So you have y in here and y in here. So the only option is to differentiate with respect to x implicitly. So you get by chain rule, what is the differentiation of sine? It is cos. So this is cos of x plus y. This becomes cos of x plus y. And then chain rule. So differentiation of x plus y. What is differentiation of x plus y with respect to x? 1 plus dy upon dx. So is this first term clear? How we get this? When you differentiate sine of x plus y, this becomes by chain rule 1 plus dy by dx times cos of x plus y. So similarly, what will be the next term? You should get differentiation of cos is minus sine. First you get minus sine of x plus y. Okay, minus sine of x plus y multiplied by derivative of x plus y, which is again 1 plus dy by dx. Yes. Equal to right hand side constant differentiated becomes 0. How did we apply chain rule here? We are applying chain rule because it's sine of x. So let me do that in detail. So for the first term, we have sine of x plus y, right? So what we are seeing is this is one variable. Okay, call this z if you want. So now you need to differentiate. I'm sorry, differentiate sine z with respect to x, not with respect to z. So sine z with respect to x, that is cos z times dz upon dx. But what is z? It is x plus y. So dz upon dx is ddx of 1 plus y, ddx of x plus y, which is 1 plus dy by dx. Again, remember, whenever you differentiate y with respect to x, we don't know y explicitly, so we cannot write any particular expression for it. All you can write is dy upon dx. You cannot write 0 or anything because y is a function of x implicitly, and its derivative is nothing more than dy by dx. There's no other way of writing it in implicit differentiation. Okay. So you have to write 1 plus dy by dx. And so that is 1 plus dy by dx times cos of z. Again, z is x plus y. So cos of x plus y. Is this clear, Parth? The chain rule part of it? Okay. Yes. Now we have wait, this is actually strange. You get this equals 0. So, that's strange. I think I've missed something here. There are some possible simplification here, I think. because x plus y and minus, yeah, here you get the same thing. So actually you're getting dy by dx equal to -1. Okay, which means actually that y is equal to minus x or minus x plus some constant. Because if derivative is -1, then the function should be minus x or at best some constant minus x. So which means y is just a linear function of x. That's not clear from here, I guess. You have sine of x plus y plus cos of x plus y, right? Equal to 1. So oh, okay, I get it. The thing is that, fine, you can write cos of x plus y as square root of 1 minus sine square x plus y. And so you essentially have something like z plus square root of 1 minus z square equal to 1. Or 1 minus z square equal to 1 minus z the whole square. So this is equal to 1 minus 2z plus z square, which gives you a quadratic equation which you can solve. So if you solve that quadratic equation, you can get something in terms of x plus y, in terms of sine of x plus y equal to something. So x plus y equal to something. So that does make y a linear function of x. So okay, in this example, although it was not obvious at first, it's actually the differentiation. The result of the differentiation tells us that we could have simplified this. Okay, fine. Let's look at one more example. Where we have, say, a polynomial. So x to the 4 minus y to the 4 plus 2x y cube minus xy square plus y plus p equals 0. Okay. So this should also be simple to differentiate. There isn't any trigonometric or exponential function or anything here. So it's just polynomials. Right? So you need only product rule and of course chain rule for the implicit differentiation. So differentiating this now, x power 4 becomes 4x cube, whereas y power 4 becomes 4y cube dy by dx. Okay, now shall I switch to this notation where I write dy by dx as y dash? Just more compact notation. So I'll write this as y dash. Okay. So 4y cube y prime or y dash plus now 2x y cube. So this needs product rule. So first, if I differentiate with respect to x, I mean differentiate x with respect to x, you get 2y cube. And then next differentiating y cube with respect to x, you get 3y square there, but 2x is already there. So 6x y square and y prime, okay, because it's implicit. Next is minus xy square. Again, you need product rule. So minus of something. Minus of y square plus, remember I've already taken the minus outside, so don't write it again, plus 2x y prime. Differentiation of y is again just y prime equal to 0. 3 differentiated becomes 0. So now you have here 4 different terms with y prime in them. So collect those together and collect the remaining terms together. So we have 4x cube plus 2y cube minus y square, which are all terms without y prime in them. And then you have minus 4 y cube y, okay, y prime is common, so I'll write that first. 4y cube, that's the first term here. I'll write plus y prime, okay, so minus 4y cube, then plus 6x y square, that's over here. And here you have minus 2x y, and here you have plus 1. Y prime is common, so this equal to 0. And so taking all of this to the other side, 4x cube plus 2y cube minus y square over here. And when you take it to the other side, there's a minus here, which I'll distribute inside. 4y cube minus 6xy square plus 2xy minus 1, right? The minus coming from taking this over to the RHS. So finally, this equal to this divided by this. So 4x cube plus 2y cube minus y square upon 4y cube minus 6xy square plus 2xy minus 1. So this y prime notation is more compact. Otherwise, you would be writing dy by dx over and over here. So in such a lengthy problem, it's better to use this notation. Okay. Of course, you can have. Let's look at a more complicated problem. So this is, both of these terms are exponential because you have x to the y, and y itself is a function of x, right? It's implicit. And y to the x, again, that is x in the exponent. And you cannot take log on both sides because there is a plus here. So how do you do this? In the previous problem, how do you get 4y cube? 4y cube is here. Y to the 4 becomes minus 4y cube y prime. And so that is over here. Okay, you understood, right? This term is this term. Okay. Okay, yes. Yes, you said take log separately. Correct. You can take log separately. So that won't be this function. So you'll have to do it separately as you'll have to just find their derivatives. So if you write z equal to x to the y, okay, so if you call this, or I'll call it u and v, okay, not the uv in uv rule. I'll just call these u and v, just two functions, okay, and we'll find the derivatives separately. So what you will get is, of course, you get du by dx plus dv by dx. equal to 0. That's what you're supposed to get. Or maybe to make this non-trivial, let me write the right hand side as x. Otherwise, you may get something trivial. So let me write it as x. So this becomes 1. Okay, so we have some interesting derivative. So the task now is to find du by dx and dv by dx. So do that separately. First, we take u is equal to x to the y. Then take log. So log of u is y log x. So differentiating, get 1 upon u du by d. Again, let me write this other notation. U prime by u. U prime denotes du upon dx. So just remember in general, if or derivative of log of y is always y prime upon y. This is a nice property to remember, very useful. So yeah, u prime upon u is equal to, on the other side, you have y times derivative of log x, that's y by x, plus log x times derivative of y, that's y prime. Okay. And therefore, u prime is equal to u times of this. But what is u? It is x to the y, right? So x to the y times y by x plus y prime log x. Okay. Similarly, v equals y prime x. Sorry, y to the power x. You cannot reuse this result by interchanging x and y because we are differentiating with respect to y. There is an differentiating with respect to x, so there is an asymmetry there. So what you get is something else over here. You cannot just, although expressions are similar, the differentiation is with respect to x. So it's what we are doing is not symmetric in the two variables, so to speak. So log v is x log y now. So you can see the asymmetry. So here you have differentiating, you get v prime upon v equal to, now x log y, when you differentiate, first you get log y and then you get x by y. So v prime is equal to v, that's y to the x, times log y plus x by y. Okay, so this is u prime and v prime. Now this plus this equal to 1. We have x to the y times y upon x plus y prime log x plus y to the x times log y plus x by y equal to 1. Okay, because it was x in the RHS, when differentiated, that gives 1. So again, collect these terms together. Wait a second, I think I forgot something here, right? Yeah, I forgot y prime over here. I'm very sorry. We are doing implicit differentiation, so you get y prime over here. And if you miss that, that's very wrong. So yeah, here you have y prime, okay? So yeah, collect these terms together. So have y prime times, this is also there, don't forget, outside, x to the y log x, and over here plus y to the x times x by y is equal to 1 minus x to the y times y by x minus y to the x log y. So final answer, I'll have to write it here. Y prime is equal to 1 minus, over here I'll combine this x to the y divided by x and write it as x to the y minus 1y. Okay, minus y to the x log y upon x to the y log x plus y to the x minus 1 x. So that is the answer. Okay, so if this is given, you have y x to the y minus. Yeah, I don't think you can get it directly, right? You cannot differentiate this directly, right? If you differentiate this with respect to x, can you write it as y x to the y minus 1? No, because that assumes it's constant, so which is not. It's not a constant, so you cannot do it that way. Although we have a term which looks like that, you also have an extra term here, which you wouldn't get from that kind of differentiation. So you have to do it this way. Okay. So I hope this answer is also clear. So now you can really differentiate any kind of function, explicit or implicit, provided it's in terms of elementary functions. If you have discontinuous functions or something, or non-differentiable functions, then you cannot, because the derivative does not exist. Or if you have some so-called special functions, which are written in terms of some other integral and so on, also then you cannot. But any function that is given in terms of these elementary functions and elementary operations, you can differentiate them. Okay, now let's have a quick look at those exercises in the remaining 1 minute. I forgot where I gave it. Right here, right. So if you find this, as usual, I'll take this to be the innermost function. So differentiating that, I get just e power x. And then differentiating tan inverse. What is derivative of tan inverse? It is 1 by 1 plus the square of that. So here in place of x, you have e power x. So 1 by 1 plus e power x the whole square is e power 2x. So derivative of tan inverse e power x is e power x by 1 plus e power 2x. No, only tan inverse has no meaning, of course. What I mean is, if you treat this as some z, so you're differentiating tan inverse of z. If you differentiate it with respect to z, it is 1 plus 1 by, rather, 1 by 1 plus z square. So 1 by 1 plus z square, where z is e power x. But then you multiply by dz by dx. So z is e power x, so dz by dx is e power x. So that is chain rule. Okay. That's why we put this box around it in our mind to perform the differentiation with respect to the thing inside the box. So 1 by 1 plus that box square. And e power x whole square is e power 2x. So similarly, if you do 1 by sine inverse x, there are two functions here. One is sine inverse, that's the innermost, and then reciprocal as a function. Okay, taking the reciprocal as a function. So again, innermost function differentiation is 1 upon square root of 1 minus x square. That is derivative of sine inverse x, right? Derivative of sine inverse x multiplied by derivative of reciprocal, if you remember, is minus 1 upon that square. What is that? Sine inverse x, the whole square. Please don't write it as sine to the power minus 2 of x. That doesn't really have any meaning. So minus 1 upon sine inverse x the whole square. So you can write it in a simpler form, but not really. Minus 1 by sine inverse x whole square times square root of 1 minus x square. You can write it in that form. So that is the answer. This we already did. So cot inverse 1 by x is similar. Derivative of 1 by x is minus 1 by x square. And then derivative of cot inverse x, cot inverse of anything is minus 1 by 1 plus that square. So 1 by x the whole square. This really can be simplified by taking LCM. And so you finally get the answer as x square upon x square plus 1, I believe. Is that right? Oh no, there's no x square. You get it as, of course, 1 upon x square plus 1. But then you notice that this is actually the derivative of tan inverse x. So what is happening? You have to remember that cot inverse of 1 by x is tan inverse of x. Because cot theta is 1 upon tan theta. So cot inverse of 1 by x is tan inverse x. So you are just finding derivative of tan inverse x itself here. Okay. 1 by cot inverse is not tan inverse. Cot inverse of 1 by something is tan inverse of that. All right. So now for today we have finished differentiation, basic differentiation. Now you have higher order derivatives, which I'll very briefly discuss, and then we'll move on to integration. Thank you.